All right, in this video, I'm going to continue to go over chapter 2.2 fixed point iterations. So the last time um, we got a question: how can we find a fixed point problem that produces a sequence that reliably and that rapidly converges to a solution to a given root finding problem? So in this example, see example 3 right here. So for given equations, and then we want to find out the unique root and close interval 1, comma 2, and then we transform the root find problem to the fixed point fixed point form x equals 0 of x, and then the thing is that there are a whole bunch of way to define 0 of x. So there's g sub 1 to g sub 5, and then these you can see that for each definitions, there were completely different reserves. See, for A and G1 is just diverse, and G2 in the case of we define G like this, and then it's undefined. Then C, the 30 iterations, we get the sequence is converts to solution of 30 iterations, 15 iterations, and the last one is best. Why? Okay. So we need to figure out the answer, right? So here, the theorem 2.3 is your fixed point iterations, the fixed point theorems. You might be the different theorem number in your textbook depending on the additional textbook. So let G is continuous function on closed interval a comma b, and it's such that the range is in the closed interval a comma b. So this is the big assumptions. We got that assumption in the theorem 2.2, right? And then suppose that there you could just g prime, and then the absolute value of the maximum, the absolute value of the derivative of g is bounded by k, and the k is between 0 and 1. So now for any number p0, which is the initial approximation, okay, the sequence defined by pn is equals 0 p sub n minus 1. This is the core algorithm in a fixed point iteration method, right? And to convert to unique fixed point p in closed interval a comma b. So now then, the let me see. So the key point is for any number p0, okay? So defined by pn equals 0, pn minus 1, converts to unique fixed point p, okay? I mean, so definitely to prove this, definitely we need a theorem 2.2, but let's see. So theorem 2.2 implied that there exists. So theorem 2.2 was about what? The existence and the uniqueness of the fixed point, right? So since theorem 2.3 has it says the hypothesis of theorem 2.3. You see function g is continuous, and then ranges in also belong to closed interval a comma b, and then the absolute value of derivative is bounded by k. These are the hypothesis exactly same as hypothesis in theorem 2.2. So theorem 2.3 guarantee that the result conclusion of theorem 2.2. So yeah, theorem 2.2 implies that there exists unique fixed point. Okay, now then, so you don't have to worry about that the existence and the uniqueness of fixed point. Now next, since G maps closed interval a comma b into itself, the sequence Pn is defined for all n which is greater than or equal. I mean here, so then what we are going to do? This one, that sequence for any initial approximation, that sequence will converge to the fixed point P. Okay, that's what we're going to prove. So now then, the since G math closed interval a comma b into itself, and the sequence is defined for all n which is greater than or equal to 0, and Pn is belong to a closed interval a comma b. Yeah, it makes sense, right? Because Pn is defined by dual Pn minus 1 for every single the x values in closed interval a comma b is function value through the function g should be belong to closed interval a comma b. That's the assumption, theorem 2.3. So Pn must be Pn must p sub n, that sequence must belong to closed interval a comma b. So we're gonna use the mean value theorems, and then see the fact that after value of the derivative of g is bounded by k. So Pn minus p, you see that now see this is pretty much that the strategy is proving theorem 2.3 is really similar to the proof of the second statement B in the theorem 2.2, right? So using the Beam-Bell theorem, Pn minus P is equal to G of Pn minus 1 minus G of P, right? Because P is what? Fixed point, right? Okay, fixed point. So G of P must be equal to P. So P can be expressed as G of P. So now then this is equal to, now you use Beam-Bell theorems, that must be equal to after value of the G prime. There you could just cosine n. By Beam-Bell theorem, there you could just cosine n such that what? The slope of the secant line, okay, passing through P sub n comma 1, P sub n minus 1 comma 0, P sub n minus 1 and P comma 0 P equals the slope of the tangent line at cosine n, which is G prime cosine n. Okay, so now then then we're gonna get this one. Okay, we'll get this one. So now then, since the absolute value of G prime is bounded by K, so we put K, and then we're gonna get that inequality. Okay, so now then what? See, the what applying this inequality, see that we got that inequality inductively gives, see, so Pm absolute value of Pm minus P is less than or equals K times Pm minus 1 minus P, that is equal to K times G of Pm minus 2 minus G of P, that is equal to K times G prime, and then by the Beam-Bell theorems, Pm minus 2, keep doing this, okay? So in the Pm minus 2 minus P, this is bounded by then K, G prime is bounded by K, so we got K squared, and then Pm minus 2 minus P, you see that this one, that is equal to, give me a second. So this one, or so we can rewrite this one as what? That is equal to what? This part is equal to absolute value of G prime cosine, right? Okay, n minus 2. I think this should be what? Just give me a second. That should be what? Let's see. That should be n minus 1, right? And this should be n minus 2. 2. Okay, cosine and then pi times, and then p. Give me a second to see. Yeah, so this should be p n minus 3 minus p. Oh yeah, p right here. By the way, that is equal to, actually I skipped one terms. That is equal to absolute value of what? G of Pn minus 3, right? Minus P is a G of P. Okay. So that is equal to this, and then this one, since the absolute value of derivative of G is bounded by K, so that one can be replaced by K, and then we're going to get the inequality this. Okay. And then we're going to get K cubed. And then doing this, repeating this one, we're going to get this. Finally, we got this K to the nth power, and then times P0 minus P. But we see that K is what? K is a number between 0 and 1. So n is increased, the K to the nth power approaches 0. And this is constant, right? So limit of K as m approaches K to the nth power times P, absolute value of P0 minus P, as n approaches infinity, 0. Okay? So we proved that what? This one, that sequence the sequence generated by this converts to P. I prove it. Okay. So now we proved that what fixed point iterations, the theoretically the fixed point iteration works. Okay. So now then you see the call over 2.4. If G satisfies the hypothesis of 2.3, then bounds for the error involved in using P sub n, the sequence, to approximate P are given by this P n minus P. Okay, so G satisfies the hypothesis of theory 2.3. Okay, and then bounds for the error involved in using Pn to approximate P are given by this. You see, like this. Okay, so now let me see. And then Pn minus P is bounded by k to the nth power over n minus k times P1 minus P0 for all n. Now let's see, proof. Okay, how come? Well, why? You see, we need to prove that one, right? So just listen, look at this, okay, and listen carefully. So in this lecture, a lot of proof. We need to listen carefully. So in the proof of theorem 2.3, since P is in A, B, Pn minus P is bounded by k to the nth power times P0 minus P. This makes sense, right? That's what we got. Oh, okay. Yeah, that's this one. We just we saw that that inequality, how that inequality is established in the proof in theorem 2.3, right? Now the P, see that P0 minus P is bounded by P0 minus A because P must be what? P is belong to AB. So it means that here's A, let's say here's A, and then here's a B. Where's a P? P may be somewhere between A and B, right? So it means that A is less than P. So P0 minus P, distance between P0 and P must be less than or equals P0 because P0 is maybe somewhere right here or right here. Anyway, between A and B, right? So P0 minus P, distance between P0 minus P must be less than or equals the distance between P0 and P, P0 and A, right? Okay. So now then, let's see. Let me see. Now, and the P0 minus P is also less than or equals P0 minus P. Yes. Okay. So now then, let me see. See. Okay. So that's why the what? This guy is less than or equals the maximum of P0 minus A and B minus P0. Okay. So now let's see. Let's see. Okay. Give me a second. Let's see. Yeah. So look at this. The second. So in this case, you might not understand that one. Let me take a look at this one detail. So here's A and then B. Okay. So now then here's let's say here's P, for example. Okay. Then maybe P0 is right there. Okay, let's say P0. Okay. Then definitely what P0 minus P must be distance between P0 and P must be greater than the distance between P0 minus A. So then that is not true, right? Right. So but P0 minus P, distance between P0 minus P, definitely P distance between P0 minus P must be less than the distance between P0 minus P, right? Then now that works, right? Okay. What about the P0 is right there? So let me use other color. Yeah, P0 is right there. Let's say P0 is right there. Okay. Then what? Definitely P0 minus P must be greater than distance between P0 minus P. So the second inequality is not true. Then but this first inequality is true. So either way, the P0 is right here, but either way, the one of them true, right? Does it make sense? So we choose the maximum. So then if we choose a maximum, for example, in that case, okay, P0 is right there. So that's not true. Okay. All right. So that so this is true is that one. Okay. In that case, then we choose see that we choose maximum, right? Then P0 minus A must be maximum, right? Okay. P0 minus A. This is must be true. This. Then what? So that inequality must be true. That inequality will be established, satisfied. I mean, now then, what about this? What about the P0 is give me a second. So P0 is right there. P0 is right there. Then this is not true, but that's true. Okay. Then choose the maximum. Yeah. Then maximum of P0 minus A and the P minus P0 going to be this. Okay. So we choose this one. So that inequality must be satisfied. It's either one. So this is not yeah, so maybe it's that cause you to misunderstand this one. Okay, maybe not end, but just think about two cases. Okay, so now the next one, move to the proof of second statement in corollary 2.4. So 2.4 was the second statement is this. Okay, P n minus P is bounded by the way, what about the corollary? What is corollary 2.4 about? Theorem 2.3 just proved that the convergence of the fixed point iterations. Now called 2.4 introduced the error bound, error bound, okay? All right, so Pn converges to P, but in a specific number of iterations, how accuracy we can expect. Okay, so if you just we iterate in the we just okay, you just complete the writing code and then you run the program and then you want to just iterate 10 times, then what accuracy can we expect? So then yeah, that's what the Coley definitely Coley 2.4 give answer for that question. So now then for n is greater than or equals 1, and then Pn plus 1 minus Pn is, you see, Pn plus 1 is what? GOPN and then minus GOPN minus 1, right? So this is bounded by k times, yeah, that's what we did, right? So, okay. So I'm not going to explain why this is about is less than or equals this, okay, anymore. Okay, so look at the proof of what? Theorem 2.3, okay? And then this is about great less than or equals to that. We got k to the nth power and then times p1 minus p0. Okay, for m is greater than n, greater than or equals to 1. So pm minus pm minus pn is equal to absolute value of pm. You see that here? What? So we add the this one minus m minus 1 plus m minus 1 minus m minus 2 plus m minus 2. You see that? Actually, we did add 0. You see? Through up to here, right? Okay. So now then, what are we going to do? So now then we're gonna the break up that inequality into what 1, 2, 3 to the actually into the breakup in every two terms that we using triangular inequality. Remember that triangular inequality? I'm sure that you learned that. So a plus b is what less than or equals what f value of a plus f value of b. Okay, so that's the triangular inequality. So now then what? Okay, now for each the absolute value, the terms can be expressed in terms of k. So for this one, Pn minus 1 must be less than or equals k to the n minus 1 times P1 minus C0. That makes sense, right? Okay. For Pm minus 1 minus Pm minus 2 is less than or equals to k to the n minus 2. And then through the what? K to the nth power, see that k to the nth power? Okay. Right. So finally, what? This is equal to k to the nth power because m is greater than n, right? So m minus 1 must be greater than or equals n, right? Okay, because you see that m is greater than n is greater than or equals 1, right? So m minus 1 must be greater than or equals n. So now then, what? First we the factor out the k to the nth power, okay? So now we're gonna 1 for here, k to the nth power, we're gonna get k, the k to the what? N plus 1, right? Through the k to the m minus n minus 1, right? Okay. So now then, what? Give me a second. What is this? This is the what, a series, right? Actually, power series, right? You see? Okay. So that's why we're gonna get this k to the nth power over omega k. Remember that power series, and then let's see. Okay. So this is that one is equal to what? Series, right? And then we see what k, not ki. There's the k. Okay. I goes 1, 0 through the m minus n minus 1, and then I to the zeroth power, sorry, not k to the I power. Okay, let me see that. All right, so that is equal to excuse me. Yeah, that's the power series. So geometric series, I'm sorry. So remember that's the geometric series, what it is. So sigma I equals 0. Let me say 1. Okay, not 0, but let's say 1 through the n, and the a times r to the i's power. Okay, this is r. Okay, if r is between 0 and 1, then that well, the series what converts to, actually this is infinity, right? It's infinity. Okay. This is 1a times, oops, 1 minus r, right? 800 minus r. Okay, so now then what? There's similarly, this one is what? Is equal to, because this is equal to sigma, right? I equals 0 through the m minus n minus 1, right? Okay, so this is in the k to the i's power, right? Okay, since k is between 0 and 1, so that is equal to what? 1 over 1 minus k. I mean, approximately, because this is not infinity, right? Okay, so that's why we got, give me a second. Oops. Yeah, that's why we got this one. Wait, yeah, this we got this one. Okay, so now then, next one. So now let's see. Yeah, by theorem 2.3, limit Pm equals P. So P minus Pn. Yeah, so I prove it. So P minus Pn is equal to the limit of Pm minus Pn, and then we can bring out limit n equals infinity. Okay, so that is less than or equals limit of k to the nth power times absolute P0 minus P0, and then times, you see that sigma right here, the finite, the sum is called the partial sum, by the way. Okay, so now then, okay, so we got that is bounded by, this one is bounded by this one. Now definitely, the finite series and infinite series, which one is greater than the other one? Definitely infinite series is greater than the finite series, so that's why we're going to get that inequality. Okay, and then this is geometry series with the ratio k. Yeah, so that series converts to 1 over minus k. So this is bounded by k to the nth power minus 1 by k, right? So now let's see g sub 1. Okay, now we're gonna see the y in the example 3. Y g sub 1 defined by like this give us the divergence. Okay, because see that let's see, g sub 1 equals 1 6, and g sub 1 of 2 is negative 12, so g sub 1 does not map closing number 1 to 1,2 to 1,2. That's the reason. Moreover, derivative of g1, which is 1 minus 3x squared minus 8x, when you find out absolute value of g derivative of g sub 1, it's greater than 1. Okay, so you know how to find the absolute value, absolute maximum, absolute minimum, right? So okay, so then since the this function g sub 1 doesn't satisfy hypothesis of theorem 2.2, okay, that's why. So, and then even the hypothesis 2.3 doesn't satisfy hypothesis 2.3. That's why the Pn generated by g sub 1 Pn minus 1 doesn't converge to P. Now B, the G2 defined by like that. Okay, G2 or so doesn't map from 1 to of closing number 1,2 to closing number 1,2. So that sequence is not defined when n is greater than or equals 3, and P0 is and the P0 is 1.5. So with that initial approximation, and the n is greater than or equals 3, that sequence is not defined. It means that P3 is what? the P3 is defined by G sub 2 of P, remember that? So P, oh, yeah, P3 is equal to G of G sub 2 of P minus P2, right? Okay. So it's not defined. It means that there that function is not defined. So that P3, yeah, we cannot figure out find out P sub 3. And then there is no interval containing P 1.365 such that the absolute value of the derivative of G sub 2 is less than 1, since the derivative of G sub 2 is 3.4. Okay, so now, this G sub 2, or so simply saying that G sub 2, this function doesn't satisfy hypothesis in theorem 2.3. Okay, so now next one, G sub 3. Also, the derivative of G sub 3 at 2 is approximately 2.12. Okay, so it means that the G prime is not bounded by K, which is less than 1. Okay, but on that interval 1, 1.5, the G3 is see that 1.5, G3 of X is bounded by 1 and 1.5. Okay, so just find out the absolute maximum of G sub 3, absolute minimum of G sub 3, then we can figure out that G sub 3 is bounded by, I mean, math from 1, 1.5 to 1, 1.5, or so G prime is bounded by, so just see that G derivative of G sub 3 is this, that is bounded by 0.6, which is less than 1. So in that, just uh, just tweak the closing interval 1, 2, the interval to 1, 1.5, then the function G sub 3 works. So theorem 2.3 confirm the convergence. Okay. So now D, it is called the bound on the let's see, G4 here. So the what? Give me a second. Now, see that derivative of G4. What is, in case? Give me a second. I forgot the, yeah, D. See, that works in that in this definition of G4, G sub 4. It works, but 15. It takes 15 iterations. So why? We'll see that. Let's see D. Where is D? Yeah, right here. So G prime, G sub 4 prime is this -5 over square root 10 times 4 plus x to the 3 half. Definitely this is bounded by 5 times square root 10. See that 5 to the 3 half. Okay, so what? Because I mean, so x can be what? The domain is closed interval 1, 2, and then the 4 plus x is in the denominator. So if we substitute the minimum x value on the domain into x, then we're gonna get the largest value as fraction, right? Largest fraction. So the minimum x value we can take in the domain closing in 1, 2 is what? 1. So plugging 1 into x, we're gonna get 5. Okay. So definitely that fraction must be greater than or equals, the greater than or equals all possible if the value of that fraction for any x value enclosed in the 1, 2, right? So now calculating this, that turns out to be 0.15. So 0.15 is what? The yeah, this is the what? That is called the bound on the magnitude. So it means that G prime is bounded by 0.15, which is less than 1, right? Okay. So now then yeah, so that's why it works out. Yeah, that's why that definition. Also, you can check the whether or not judicial for mass from 1, closing 1, 2 to 1, 2, but I believe that it is. Okay, it does. Judicial for mass from closing number 1, 2 to closing number 1, 2 itself, and then G prime is bounded by 0.15. Yes, so it works. But it takes 15 iterations. Now then, second, last one. Let me see. Let me see. So now then, by the way, so in C, how come? So you see, in that one, let me see. In that definition, that in this one, G sub 3 in C, it takes 30 iterations. Why? Because you see that G sub 3 is bounded by 0.6, is close to 1, right? But the 0.5 much far away from 1. I mean, much close to 0. I mean, so that, decay in D is much less than decay in C. That's why you see the G sub 4, that definition in that case, we got less iterations to convert to P than G sub 3. Okay. So now E, that's the best. Why? So GPN is defined by G sub 5. I mean, this one, okay, I told you the top one, the fraction, top one is the just function f of x, denominator is f prime, right? Okay, much more rapidly than our other choices. Why? Okay, that's the next topic in this section 2.3. Okay, I'm gonna cover that one next time. Okay, let me stop here.